This is the presentation for our paper on a new neural architecture search space that we call einspace. NAS consists of three components: the search space of all possible architectures, the search strategy for exploring this space, and the performance estimation strategy for scoring architectures. This paper focuses on developing and evaluating a new search space focused especially on expressivity. It turns out that many of the common search spaces in the field are narrow, with many high-performing architectures clustered at the top. This means that even the super simple random search strategy performs on par with state-of-the-art algorithms. Furthermore, these spaces tend to be based on convolutional networks, which severely limits the type of architectures that can be found. On the other hand, the search strategy matches much more in the very large search space of AUTOML24, which is built from individual lines of code. The high complexity and expressivity of the space is highlighted by the fact that it took thousands of hours of compute to find even a simple network. One downside here is that the search starts completely from scratch. So what we want is a search space that is, one, expressive enough to contain diverse good architectures beyond common nets, and two, not so huge that searching the space is super slow. So let's take a look at how we've tried to construct such a space. The fundamental operations in einspace are built around a single parameterized linear layer. Other operations enable branching structures and more complex components like convolutions. We place these functions into four groups: branching, aggregation, routing, and computation. The branching group contains operations that clone a tensor into multiple identical tensors or group a tensor along a specific dimension. The aggregation group merges multiple tensors into one by matrix multiplication, addition, or concatenation. The routing group contains the im2col and call2im operations that enable convolutions, as well as permute operations that swap the axes of a tensor. Finally, the computation group contains the linear layer, normalization, activations, and positional encoding. Functions are used to form macro structures using different modules. The sequential module composes two functions, one after the other. The branching module has a branching function that splits the input into multiple branches, which are later merged into one output by an aggregation function. And the routing module composes a routing function, an inner processing module, and then a final routing function. Together, these modules can be combined in complex and recursive ways to form all kinds of structures. Inspired by the amazing work of Crowley et al., we formulate einspace as a context-free grammar. The grammar is listed in full here, but for full details on it and its extensions, please see the paper. Within the space that we have presented, we can represent many common state-of-the-art architectures like ResNets, transformers, and MLP mixes. And in order to explore our search space, we look at a few common search strategies: random search, which tends to be competitive in other spaces, and evolutionary search, where we see the initial population, either with randomly generated architectures, ResNet 18s, or a mix of ResNets, wide ResNets, vision transformers, and MLP mixes. Now let's look briefly at our evaluation of einspace. Our experimental section uses a very broad set of datasets from two benchmark suites, which includes standard computer vision tasks, but also tasks from audio, astronomy, and fluid dynamics. And while we don't go into all the results here, I'll summarize our findings. We find competitive results across a diverse set of tasks with some new state-of-the-art results, highlighting the value of our highly expressive search space. And we report success from initializing the search with existing architectures. We also find some novel architectural components not possible in other search spaces. And here are some examples from the ADNIST, language, and geoclassing datasets. Thank you very much for listening, and I hope to see you at our poster.